Our next speaker is Pascal Lee. Pascal Lee studied physics and geology at the University of Paris, got his PhD in astronomy and space sciences at Cornell. His research focuses on water on the moon and Mars, the human exploration of the solar system, and SETI. He is also a helicopter flight instructor and a space artist collected worldwide. The title of his talk is Alone in the Milky Way. Pascal, it's all yours.
Good afternoon, everybody. I'm very sorry I can't be with you in person, but I'm very grateful to the IRG and to Andrew Higgins for organizing this symposium. So thank you for having me. This talk is a little bit peripheral to the central topic of interstellar travel. But it is a back of the envelope estimate of the number of advanced civilizations in our galaxy with a minimal number of assumptions. And I guess the end message is that we're unlikely to run into anybody as we proceed with interstellar travel. But let me try to make this case more specifically. So we live in a large galaxy. The Milky Way galaxy has about 100 billion to possibly 400 billion stars. And, if each star had roughly 10 planets or planetary bodies around it, including large dwarf planets, then we would be looking at roughly 1 trillion planets in our own galaxy. And that's a staggering astronomical number, although put things in perspective, it's still about 30 times less than the U.S. national debt. But moving on, there are about 100 billion galaxies in the known universe. And so if each galaxy had about 1 trillion stars, we're looking at roughly 1 mole, the Avogadro's number of planets in the known universe. So it is a very large number. Now, we are wanting to be open-minded about how many advanced civilizations there might be in our galaxy. And so we tend to be open to the idea that there would be many across our galaxy. And, in popular culture, we are bathing in Star Trekian galaxy or Star Warsian universe. But even though we are open-minded about this and think that we, might be in good company out there, the odds of there being many advanced civilizations in our galaxy at this time are actually likely to be small. And I'm going to try to make that case today. So here is the Drake equation. I probably don't need to go over it for most of you, but for the sake of completeness, the number large, capital N, is the number of advanced civilizations in our galaxy. And that number can be estimated by this formula, which is mathematically very simple. It's the multiplication of 7 terms, the rate of star formation times the fraction of stars with planets, times the number of planets within each planetary system where the environment would be suitable for life. And by that, we understand where liquid water is stable on geological timescales, times the fraction that actually see life emerge on them, times the fraction of those with life where the life actually becomes intelligent, and we'll try to define that, times the fraction of those planets with intelligent life on them that become an advanced civilization, times the longevity of an advanced civilization, the average longevity of an advanced civilization, which of course is a very difficult number to know. Currently, if you look at maximum estimates, so to speak, the rate of star formation might be cranked up to 50 or so. If you, all these F terms are fractional numbers. numbers, but if you max them out, they are essentially equal to 1. If you posit also that there's at least one environment that's suitable for life per planetary system, that puts n equals e at 1. With a longevity, if you're optimistically suggesting that we might consider the fact that since we have become Homo species, since Homo erectus, essentially for the past 2 million years, the longevity of a civilization might be considered to be about 2 million years. Then n could be about 100 million across our galaxy, and the nearest civilization would be less than 10 light years away. More commonly, the rate of star formation is roughly 20 or so, at least in the earlier part of the Milky Way's life. The longevity of a civilization is often suggested to be about 50,000 years or more. That would yield about 1 million civilizations in our galaxy, and the nearest one would be less than 10,000 years. So it's on those numbers that the SETI effort that focuses in our own galaxy are justified. In this talk, I'm going to review every one of these terms of the Drake equation and use the Earth as the single data point when it is the only data point we have, with the assumption that what the Earth has experienced is representative of essentially a mean. That's a big assumption, but that's the assumption that's going to go behind these numbers. I'll try to speculate as little as possible by considering factors that are beyond the single data point that we have, which is, once again, the Earth. Now, meanwhile, there's the Fermi paradox, which I think you're all familiar with. If n is a large number, where's everybody? And here are a number of explanations that I won't have time to go over, but essentially, these explanations go this way. N is actually a large number, but it just appears small for a number of reasons. And I'll just pick a few. Interstellar communications and travel are too difficult, so they're not worth pursuing for some of these civilizations. Or the SETI effort is young, and so we've only just started to look. Maybe SETI is misguided. We're not doing the search right. Or SETI is suppressing evidence, and we actually have found them, but this space is intentionally left blank. So aside from the fun interpretations, the point is there are many possibilities in theory as to why there could be a Fermi paradox and why n could be large, but would appear small. Now, the rate of star formation, we actually have a pretty good handle on it. It has been evolving over time in our own galaxy and in all galaxies. Today, in our Milky Way galaxy, it's of order 6 to 7 stars per year. In the Andromeda galaxy, which is a large galaxy next to ours, the rate of star formation seems to be even lower than that, somewhere between 2 and 3 stars per year. But earlier in the history of the Milky Way galaxy, the rate was substantially higher by about an order of magnitude. And so for the Milky Way or so, the estimates of star formation rates today range from in the earlier part of the history of the Milky Way, range from somewhere between 1 and 40 stars per year. The single-digit numbers being closer to current rates of star formation, the higher numbers being more characteristic of the earlier history of the Milky Way galaxy. And, these numbers are still small compared to the so-called starburst galaxies, where the star formation rate can be 100 to 1,000 times greater than the single-digit numbers that we see here. But I'm going to suggest that we use 20 as an average star formation rate characterizing the bulk of the history of the Milky Way, but especially its earlier parts, its earlier history, since we result from that star formation rate specifically. So R sub star, roughly 20. Even if it were 40 or 100, you'd be off by just a factor of 5. It's not like it's hundreds or thousands, as in starburst galaxies. We're still in the rough ballpark here with 20. What fraction of stars have planets? Well, we have several lines of evidence for that. We have theoretical modeling and our understanding of how planets form, which have predicted that many stars, especially main sequence stars, have planetary systems around them, even before we found exoplanets. Then we've actually seen planets in the stage in the process of forming. So this is a recent image from the Subaru telescope of AB Aurigae showing uh, planetary formation at distances of similar to Neptune's orbit or even beyond around the nearby star. And then the Kepler mission, of course, was a big revolution. It showed between 2009 and 2018, over the course of 9 years, it looked at about 500,000 stars uh, within a range of about 3,000 light years in a specific direction from the sun along the Orion spur in our Milky Way galaxy. And that search has resulted in the discovery of about 3,000 well-characterized exoplanets and up to maybe 5,000 candidates as well. So so planets are common. Planets are common around nearby stars. We are looking here at also planets that are known around the 10 closest, the stars within 10 light years of the Earth. And most of them have planetary systems around them as well. So F sub p, while it is not one, because we can't claim yet that every star will have planets around it, is probably not a small number. And so we're going to suggest that F sub p is about 50%. 50% of stars out there will have a planetary body around them, or planets, or more than that. Now, within a planetary system, how many environments might you have that are suitable for life? Well, that is often limited to being described as whether or not the planet is within the Goldilocks zone, so the proper range of stellar distances where liquid water would be allowed to survive and be stable at the surface of the planet. And so if you have a hotter star like the sun, a more massive star, then the distance actually is somewhere between Venus and Mars. And sure enough, we're within the Goldilocks zone for that class of stars. For red dwarfs, of course, the Goldilocks zone is closer in. And it's only then that you could have temperatures that are warm enough for liquid water to be stable over time. But the Goldilocks zone, as defined by a stellar-centric distance, is only one way of identifying a possible habitable zone within a planetary system. Each planet could also have sub-environments that would be stable over time. So the surface of Mars today is considered to be sterile and also devoid of liquid water, but at least clean water. But the subsurface could be liquid as you go down and the geothermal gradient increases with depth. Down to a depth of about anywhere from 2 to 10 kilometers, one is expected to find liquid water aquifers in the subsurface of Mars. There could also be hotspots nearer the surface with volcanoes. Most recent volcanic eruption on Mars in Elysium is dated to only 50,000 years ago. So for all intents and purposes, Mars is still an active planet. Therefore, in parts of the planet, the shallow subsurface could also have stable liquid water over geologic timescales. And in that sense, the subsurface could be habitable as well, almost regardless of your heliocentric distance, actually. So this is just a depiction of how we might explore one of these volcanic caves on Mars in the future. The giant planets have also been speculated to have possibly habitats in their atmospheres, in a zone where the pressures and temperatures are not too high, where you're also shielded from radiation by a thick atmosphere, and at the same time where you might have nutrients being convected up and down through the atmospheric column. And so Carl Sagan, for example, and Edwin Salpeter have hypothesized that there could be floaters and other organisms living in the atmospheres of these giant planets, in particular Jupiter. The oceans that are known now to exist in the subsurface of icy moons of the giant planets, Europa, are also potential habitats. So here's a depiction of a giant creature in the oceans of Europa. And here is also Enceladus, where the crust is less thick than on Europa and the ocean is less deep. The crust actually is thicker than on Europa. On Europa, the crust is maybe 20 to 25 kilometers thick, but the ocean is about 100 kilometers deep, so between 60 and 150. Here on Enceladus, it's sort of the reverse. You have a thick, icy crust of 30 to 40 kilometers, but through which apparently liquid water is jetting out and essentially turning into vapor plumes above the surface, plumes of condensates. And the ocean from which these plumes are jetting out from could be 10 kilometers or more in depth. Now, so therefore, within a planetary system, you could have many more habitats than just those defined by your stellar distance. Beyond that, within our galaxy, there are zones within the galaxy where life is unlikely to exist at the surface of planets. Uh, and this has to do with the fact that gamma ray bursts, most of which result from supernova events, but there are other origins for them as well, are particularly frequent near the center of the galaxy. And so if you look at the x-axis here, you have the distance from the galactic center. Near the center of the galaxy, you have very frequent gamma ray bursts. Farther out, you have infrequent ones. The Earth is in a zone where the probability of life at the surface from essentially this exposure to galactic gamma ray bursts has a probability of about a half. So, we are lucky in that sense, but it's only really farther out from where we are from the galactic center that the probability of life being present for long periods of time at the surface of these planets is good. Closer in, it gets less and less good as we're near the center of the galaxy. So there is also this extension, if you will, of a Goldilocks zone within galaxies as well. You want to be far away from the GRBs of your galaxy. Now, how many environments could be suitable for life, therefore, in a planetary system? Well, we're going to suggest that given the range and possibilities of finding a habitable zone in giant planets, in the subsurface of smaller worlds, on planets that are within the Goldilocks zone, we might be looking at n sub e about 1. Which fraction of these would actually have life? Well, Harold Urey and Stanley Miller did a famous experiment many years ago. They synthesized amino acids by zapping, reducing, in this case, atmospheric gases of the early Earth. They were more likely made of CO2, the gases of the early Earth, but in those days, this was the assumption. And amino acids formed immediately. And since their experiment, we've gotten so far as being able to synthesize and have self-replicating RNA enzymes. But there are major steps here in the origin of life that are still not replicated in the lab, not understood. We think still that the origin of life started mostly in settings such as oceanic hydrothermal vents. But the key thing to note here about the origin of life on Earth is that life appeared very early in the Earth's history. It is something that is recorded in the earliest sedimentary rocks that we have any remains of. At this point, they're no longer sedimentary rocks. They are recrystallized, metamorphic rocks, but they were sedimentary settings at first. As the oldest originally sedimentary rocks that we have fossil records in them. And so this is really quite remarkable. What this tells us is that life started early. The life itself is likely to be relatively easy, so to speak, when conditions are right. And so this is again illustrated here with the entire column of the Earth's history. You can see that the oldest rocks known on Earth essentially coincide roughly with the earliest record of life on Earth. Okay, so the thinking here is that life is not difficult to achieve. It appears early as soon as conditions are right, without claiming that F sub L is 1, which would mean that life appears every time where there's stable liquid water. We're going to suggest that it's going to be about 50% or so sub L. What fraction of this evolves into intelligent life? So I'll define this for now as the emergence of Homo erectus. This is the first being on Earth that really was able to start to master its environment and create technology, improving it from generation to generation that otherwise, did not exist as a process in nature until then. We're not talking about the beaver building a dam. That's innate in the sense that there's no improvement in the technology that is used to build a dam from generation to generation. This is something that is inherent to the species and built over many generations of the species evolving. We're talking about intelligent life as being an adaptation that each individual within a species can now come up with to improve the fate of the rest of the species. And so Homo erectus mastered fire, at least was able to control fire and carry it around. It also started using tools. And this happened roughly starting 2 million years ago on the Earth. This is Mr. and Mrs. Homo erectus, I guess, defending their property. Uh, Maybe there's a predator there or a taxpayer. A tax collector. But in any case, intelligent life appeared, if it appeared 2 million years ago by this definition, appeared very late in the history of our star. 2 million years ago is essentially the present, geologically speaking. And the sun, which will have a lifespan of about 10 billion years, essentially intelligent life appear already halfway through the life of our star. So the implication here is that the emergence of intelligence is not something that is rapid. At least, once again, we're using the Earth as the single data point we actually have and assuming it's general. That's a big assumption, but that is the assumption we're using. And so then it took pretty much half the life of our star for intelligent life to just appear about 2 million years ago. Now, if you look closer in, you can see that there are large species of animals like dinosaurs and mammals that have roamed the Earth for over 200 million years or so. And they have not produced anything that would be defined as intelligent in the sense of being able to really modify your environment from generation to generation. And so this is something that really is special and appeared really with just Homo erectus. There was no directed evolution towards that capability. It was definitely happenstance. The dinosaurs were wiped out, as we know, by the Chicxulub impact 66 million years ago. And that is actually the opportunity that allowed mammals to proliferate and eventually give rise to Homo erectus and Homo sapiens down the road. So very happenstance, very circumstantial, and fortuitous. And so it's difficult to characterize the fraction of intelligent of life that will actually become intelligent life. But we're going to suggest that if you divide the median duration over which Homo erectus or Homo sapiens has been around on the Earth, so Homo erectus more specifically, about 1 million years or so, divided by the age of our planet, that gives you a sense of how long the Earth has been occupied by intelligent life. If you were to sort of run into the Earth randomly and up to this point and see what fraction of our Earth's history has been occupied by intelligent life, you'd come up with about 2/10,000 for F sub I. Okay. Now, any number F, of course, that is small is going to bring down N. And this is really where the idea of N being possibly really small comes from. Life itself appears very early and therefore almost automatically, essentially, whereas intelligent life appeared very late under very specific circumstances and therefore is probably rare. And so this is reflecting it's an attempt at quantitatively reflecting that rarity. So what fraction then of intelligent life becomes an advanced communicating civilization? So we define an advanced civilization compared to just intelligence as the understanding of electromagnetic waves and their propagation through space, which is essentially when we became capable of radio communications and, as a species, and had the ability to start communicating with others potentially if they were using radio waves as well. And so that happened in 1865. 1865 is when James Clerk Maxwell came up with Maxwell's equations. And so from that day on, we were an advanced civilization, if you don't mind my characterizing things this way. Whereas before that, we were an intelligent civilization, but not necessarily very advanced. But from James Clerk Maxwell onwards, we understood EM waves and could be considered a a civilization that was technically capable of interstellar communication, etc. So the time that elapsed between Homo erectus seen here roughly 1 million years ago, this is the Sangriran 17 Java man, and James Clerk Maxwell was about 1 million years. You can see that although our understanding of light, radio waves, and electromagnetic wave propagation has increased dramatically, uh, barbering has not. Now, there are, however, many possibilities through which the emergence of an intelligent form of life might not automatically turn into an advanced civilization. Okay. And again, an advanced civilization is a civilization that's capable of interstellar communication, but doesn't necessarily practice it. Okay, so that's very important to sort of as a nuance. Uh, but there are species or settings that we can imagine where an intelligent society could emerge, but where it would essentially not have the opportunity to become an advanced civilization because it would be very difficult to even come up with Maxwell's equations in our understanding of the world. Orcas, for example, there might be very many ocean worlds across the galaxy with very large, intelligent creatures like orcas that are very social. But if you can't see the night sky, if you can't launch rockets and have space telescopes, you're going to be very limited in your understanding of the universe. And also, you might not be using electromagnetic waves to communicate. So that is going to be a caveat limiting the progress from being intelligent to becoming an advanced civilization. You could also live on a planet that's constantly hazy or in jungle worlds where doing astronomy could be precluded. And so you would lack that perspective essentially for a long, long time. You might also be living on a planet where the gravity is just so high that the rocket equation won't let you launch anything using chemical propulsion. And so that could be a real showstopper for a long, long time as well for many societies. So ultimately, how many intelligent societies might become an advanced civilization? We're going to suggest that it's maybe 1 in 10. In other words, there are many ways in which you could be intelligent. 9 out of 10, roughly 9 out of 10 ways you could be intelligent, but not turn into a civilization that comes up with Maxwell's equations. Whereas, but you're still not anywhere close to zero. I mean, 10% is a decent number. Finally, the longevity of civilizations. This is the Valley of the Nile, where essentially human civilization can be considered to have sort of really started as in earnest as a civilization. Although we're not starting with a world that was just James Clerk Maxwell, but overall, if we consider ancient Egypt to be the dawn of human civilization, then we've been around for roughly 5,000 years. But there are many ways in which a civilization could be put to an end. It's not necessarily something that will evolve and last for forever. And of course, our big questions as to whether or not we could even achieve geological timescales in terms of our survival as a civilization. So meteorite impacts, for example, could be one way we get wiped out. Uh, uh, the overpopulation of the Earth could be another way we get wiped out. The Earth is able to support large populations, but it also takes very careful management and organization. And so if we have management failures or organizational shortcomings, then we might not be able to take full advantage of what the Earth can produce and support in terms of population. There could also be pandemics, and I don't need to stress this point, but could get wiped out by pandemics. There will also be world wars that could also be essentially civilization resetting events. It's hard to imagine a world war that would get to the point where nobody would know about Maxwell's equations anymore, but it's conceivable. So we should be careful about that. And then finally, once again, there's no telling how long we are supposed to last as an advanced civilization on our planet. It could be that we're just going to be a blip in the geological column where, ultimately will be remembered as a layer of rust known as the Anthropocene in the geologic column of our planet. But hopefully we have a brighter future than that. So we can always speculate. And this is where there's a lot of speculation about, well-thinking people who are suggesting we could maybe survive a million years or so. It's unclear to me that we will or could. We're now global, high tech, and we have the ability to self annihilate. And so I'll be generous by suggesting that, keeping to the rough order of magnitude we've survived so far, that we might be able to live 10,000 years as an advanced civilization before somehow destroying ourselves or having a major resetting event. I don't mean to be pessimistic, but there's no grounds to really think that we could live a million years either. So I think this is just building on our past history. One should bear in mind that cultures historically have not lasted more than 500 years or so, typically to 5,000 years. So 10,000 years overall as a lifespan for an advanced civilization is something that could be it. So if you plug in all these numbers, what do you get? R sub star 20, F sub P 0.5, N sub E 1, F sub L 0.5, F sub I 0.0002, F sub C 0.1. Longevity of a civilization 10,000 years. You get N equals 1. And of course, I'm not expecting anybody to believe, I don't believe, that we're necessarily exactly 1 in our galaxy. But the point is, we're not a million. We're not 100 million. We're not, even 1,000. As far as we can tell, what this message is here is that advanced civilizations are probably rare. And that's because they're not a normal outcome of the evolution of life. It takes circumstances that were quite exceptional on Earth for it to emerge and even ever show up. I'm using a color code to indicate the orders of magnitude of uncertainty as well within each term. The terms in white have about an order of magnitude in uncertainty.
Haskell, I'm afraid we're running low on time.
Okay.
Could you wrap it up here in the next minute or so?
So the color code is your order of magnitude. I'll skip this. Uncertainty. So if N about 1, what does that mean? We could be rare and special, even though we're not created or intended. We should behave responsibly, obviously, and not expect neighbors to help. The Milky Way could be teeming with life, just very few advanced civilizations. And so there might be many ocean worlds out there with lots of animals, but that's it. Now, in the bigger picture of the universe, where there's 100 billion plus galaxies, we could be in very good company, even if there was just one advanced civilization per galaxy. This is a chart showing the number of galaxies from us per bin by essentially millions of light years away from us. So, for example, there are 88 galaxies that are within between 32 and 34 million light years from the Earth. Okay, for the peak point. This is a histogram, and this tells you that within 2 million light years of the Earth, there's about 60 galaxies, and within 33 million light years, there's about 1,000. We should focus on these galaxies, I think, more than within our galaxy itself, or do at least both in our search for signs of extraterrestrial intelligence. It doesn't mean we'll be traveling to them anytime soon, but that would be one way of increasing our chances, I think, of detecting something. This is the Andromeda galaxy, actually seen with its actual angular diameter in the night sky. The moon is about half a degree in size. The Andromeda galaxy is about 3 degrees across, so 6 times wider than the moon. If only it were 2 million times brighter than it is, we would see it this way, but it's not. So it's because it's very dim. We don't see it with the naked eye. Well, it's not the peripheral parts with the naked eye, but it's actually a very large object. It's the largest astronomical object in our night sky, the Andromeda galaxy. And so this is just to suggest that we renew our search for ET signals from the Andromeda galaxy. Even if there were just 1 or 2, we might have a better chance of detecting it. I'll leave it at this. Thank you very much, and sorry it took so long.
I'm afraid we don't have time for questions, but thank you for that very good talk.
Thank you.